Thank you, and good morning, everybody. Today I'm going to talk about my research I'm doing in my PhD. I'm a part-time student PhD at UCL, and it's focused on online tensor learning for spatial temporal financial market prediction. So what I do in this study is actually using tensor and the spatial temporal model to predict stock prices. The reason is why combining all this together. I'm going to give you the reason just to let know everybody that financial markets are significantly important for investment decision making, but it's one of the most challenging tasks as the market to predict, as the markets are affected by multiple factors. So what are the motivations? Well, most of the lecture review focus on batch learning and less on online learning. So online machine learning is a method of machine learning in which the data become available in a sequential order. It is used to update our best predictor for future data each step, as opposed to batch learning techniques, which actually generate the best prediction by learning on the entire training data set at once. And online learning is also used in a situation when it's necessary, for example, for the algorithm to dynamically update to the new pattern in the data, or when the data itself is generated as a function of time, such as, for example, stock prediction, in this case, stock price prediction. In recent years, there have been an increasing number of studies treating financial time series as a spatial temporal time series. However, due to the difficulty in identifying contiguity, so deciding a metric distance, they actually work in the financial market environment because it's not quite an easy task. Spatial temporal models are not being adequately explored in the financial world. And to stay in the field of the spatial temporal model, only a limited number of models are actually able to capture correlation across variables, space, and time simultaneously. So that are the reason why I decided to study this field, and came out with my research. The figure here is just illustrate the framework of my research. So we can have some data that are actually represented from stocks, the stock prices or macroeconomic data. When I say macroeconomic data, they are called economic indicator like CPI, GDP, PPI, all this kind of stuff. So we do a normalization for the data, or we process through interpolation, because some macro data, for example, can come in different formats and they are published at different dates. So one can be quarterly, one can be monthly. Then we have a spatial weight matrix that's actually a distance, and it can actually be calculated on the location, so the physical location, or calculated as a financial distance. Once we have this variable, we use a tensor in the form of autoregressive model to predict financial time series and compare the online version with its, of course, batch counterpart, and with a simple vector autoregressive that's only taking consideration temporal variable without the spatial component. So to be more specific, we have 3 different spatial weight matrices. One is based on location distance. As underlined from lecture review, there are many support for theory that geographical distance matter when you have to deal with correlation in the financial market. So we compute a spatial weight adjacency matrix based on geographical location of each country, depending on the geodetic distance between each country. In order to do so, we just employ the Haversine formula to calculate the distance that we use the geographical coordinate of the main stocks exchange in Europe. However, some studies reject the hypothesis that spatial location matter, so the physical location, and propose the use of something that they call financial distance. One example of that, it can be the correlation distance. So it's just a pure correlation reshaped as a distance. What's the problem with that? A limitation with the correlation distance is connected to the fact that Pearson correlation only measure linear relationship, but at the same time is actually the dominant tool that's used in financial analysis. So even if violated evidence of nonlinearity in the financial market, that's one of the problems in the financial market. That's why it's so difficult to predict. So this problem has been addressed by swapping the Pearson correlation coefficient with Moodle information, which permit to take into account the nonlinearity relationship between variables. However, even here you have some few disadvantages of using Moodle information, such as whatever the relationship, it's positive or negative. Information cannot tell you that. As an alternative, I just decided to use a similarity measure, integrated the correlation-based distance and the maximum information coefficient, denominated MIC. That is essentially an information theory-based measure of association that can capture a wide range of functional and non-functional relationship between variables. So how the model works in a very few words. We formulate the financial prediction task as a vector autoregressive in an online tensor form. Tensor are higher order generalization of vector and matrix, which have achieved a great success in the field of spatial temporal prediction. The main model used here is called ALTO, ROSU 2016, and aim to dynamically update the tensor while preserving low-rank structure. A low-rank tensor is essentially a higher order generalization of matrix factorization. And the intuition behind this model has two forms. Instead of decomposing the original tensor, we keep track of a low-rank component at each interaction, that's why online, which allow us to perform a decomposition on a much smaller tensor. And on the other hand, because the mathematical problem of low-rank projection is that actually gets stuck in the same low-rank space, we use randomization techniques to jump out from the same low-rank subspace. We apply this model to stocks and macroeconomics data. Here I just present the stocks data that employ daily data that contain a sample from May 2016 and April 2017. So there are around 2,798 data points for stocks. Each stocks belong to their own country index. So as example, we have one stocks that belong to the healthcare index in France, Germany, Switzerland, and go on. Same concept for telecommunication, consumer discretionary, financial services, and basic material. So you actually have 5 variables, 5 countries by 5 sector by 8 countries by 2007, almost 3,000 points. So when we test the model with this data and compare the online learning against the batch and the distance, we actually can see that from the location side is the one that actually perform less compared to financial distance. And however, it does show us that spatial temporal model actually has an advantage on just using temporal variable. And we can see that the online learning is actually overperformed compared to the others. At the same time, I have to say that doing online learning compared to batch learning is much, much, much faster. So that can be one of the advantages. So as a conclusion, it proved that different spatial relationship method will affect the performance. So according with which distance or spatial weight matrix we use. In this case, the online learning prediction has a higher accuracy than batch learning, no matter which spatial relationship method it's used. And this model can be used for more advanced prediction method for stocks. So for example, as a future work, I put it identify more financial distance or investigated more online tensor decomposition competition. Why identify more financial distance? Because for example, one can use something that is called FDI in finance. So there's actually it's foreign direct investment. So how one company trade to another, how they do investment. And then can use spatial temporal model there and create spatial distance there. At the same time, completion, tensor completion is actually when you don't have data. It's actually quite common in financial world that you have missing data, so how the model can adapt to that, or how can we solve it. Thank you, I hope I was in time. Thank you, everyone.
So we've got a question in the chat already from Francisco, who said, could you elaborate on how you deal with spatial dependence and potential endogeneity problems in the estimation process?
Yes, well, spatial dependency, what we actually do here is, at first we calculate it on the correlation distance. We use the main stocks index. Can you still see my presentation?
Yeah, you'll see the presentation.
So we have the list of countries like France, Germany, Switzerland, right? And then to calculate this financial distance, correlation distance, we actually take the main indices that represent the main stocks and change. We calculate the log return from them, then we calculate the correlation, and then based on that we can create any correlation with this distance. This can affect the way how you calculate it and the dependency in between them. So for that reason, this is just the main starter to actually come out with more advanced and more suitable financial distance to be applied in the model. So it's just a very basic one.
I think actually your answer there might partially answer the next question, which is from Nick, asking what is driving the spatial structure in the data? That's, yes, is the spatial variable. So it's actually how you define this spatial weight matrix that actually affect the prediction of the model. So that's one of the very interesting things that I would like to develop and investigate more.